Imagine holding a piece of our solar system's ancient past in your hand, a relic that could rewrite our understanding of how life began. That's the incredible reality for scientists like Michelle Thompson, who are studying pristine samples from the asteroid Bennu, returned by NASA's groundbreaking OSIRIS-REx mission. But here's where it gets controversial. These tiny grains of rock are challenging long-held assumptions about how we interpret the data gathered from millions of miles away. New findings from this first-of-its-kind NASA mission are revealing the precise reasons why the surfaces of certain dark, carbon-rich asteroids reflect light in different ways, appearing more red or blue to our telescopes. This isn't just an academic curiosity. Understanding this spectral fingerprint provides a profound window into the evolution of all rocky bodies, from asteroids to planets, throughout our solar system. And this is the part most people miss. This knowledge is the key that will unlock the future of space exploration, enabling astronauts and robotic prospectors to select asteroid targets for research or resource mining with far greater confidence and accuracy. Associate Professor Michelle Thompson of Purdue University is a leading expert on space weathering, the complex process by which the harsh environment of space alters the surfaces of airless worlds. She is a key member of the international team studying the Bennu samples. The OSIRIS-REx mission, Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer, represents the culmination of over a decade of work by hundreds of dedicated professionals, all focused on answering fundamental questions about our cosmic origins. Sample return missions are the absolute cornerstone of planetary science, Thompson explains. They provide us with direct, tangible snapshots of the chemistry and composition of our infant solar system. We are essentially inventorying the original building blocks of the planets. By comparing Bennu's samples to those from Japan's Hayabusa missions, we can finally understand how these asteroids change over time and, crucially, calibrate what we think we see from Earth with what is actually there. This latest study is one of 3 major papers based on the initial analysis of the Bennu samples. Together, they paint a picture of an asteroid that is a fascinating mixture of materials from across and even beyond our solar system, a celestial rubble pile whose history has been dramatically shaped by both ancient water and relentless space weathering. Now, let's tackle a puzzle that has intrigued astronomers. We can't possibly visit all 1.45 million known asteroids, so we must rely on telescopic data. A natural assumption was that 2 similar asteroids, Ryugu, visited by Hayabusa 2, and Bennu, both carbon-rich rubble piles from the dawn of the solar system, would look identical to our instruments. But they don't. Ryugu appears slightly red, while Bennu looks blue. The burning question was, why? We thought the difference might be due to them weathering in space in fundamentally different ways, says Thompson. But the samples themselves have revealed a stunning truth. The processes are actually very similar. The difference in their color isn't about a different process. It's about them being at different points in the same cycle. Rubble pile asteroids are constantly churning, periodically refreshing their surfaces. Grains from Bennu's surface have been exposed to space for tens of thousands of years, much longer than those from Ryugu. We are simply seeing different chapters of the same story. This ability to ground truth our remote telescopic data with actual physical samples is a revolutionary step. It allows scientists to confidently extrapolate their findings to a vast number of other asteroids and airless bodies, like some moons and dwarf planets, transforming our understanding of the solar system from a distance. Perhaps the most electrifying discovery, however, involves the ingredients for life itself. Earlier this year, scientists reported finding a suite of salts and phosphates in the Bennu samples, compounds that are absolutely critical for life as we know it, playing key roles in metabolism and DNA. This is evidence of an ancient brine, a salty water environment that would have been a perfect cradle for kickstarting the prebiotic chemistry that eventually leads to life. When we examine the organic molecules from Bennu, we are essentially looking at the potential starter kit for life on early Earth, Thomson states. We won't find life itself, but we are cataloging the very building blocks that could have evolved into it. These ingredients exist on Earth today, but they have been utterly transformed by billions of years of geological and biological activity. Bennu's samples, by contrast, are a pristine time capsule, preserving a frozen moment in time before the planets even finished forming. So, what's the controversial takeaway? Some might argue that investing billions in returning mere grams of space dust is not worth the immense cost. But is there a price tag on understanding our own origins? But data from Bennu forces us to reconsider everything we thought we knew about interpreting asteroids from afar. Do you believe the profound insights into the genesis of our solar system and the seeds of life justify these ambitious missions? We invite you to share your thoughts and opinions in the comments below. About Purdue University. Purdue University is a top-ranked public research institution renowned for its excellence at scale. Consistently ranked among the top 10 public universities in the United States, Purdue provides world-class education and research to over 107,000 students across its campuses, demonstrating a deep commitment to affordability and accessibility. Purdue's main campus has held tuition rates steady for an important 14 consecutive years. The university continues its pursuit of groundbreaking innovation through major initiatives like its comprehensive urban expansion, the Mitch Daniels School of Business, Purdue Computes, and the One Health Initiative. The research paper, Sulfide Minerals Bear Witness to Impacts Across the Solar System, is published in the journal Nature Communications. 10.1038/S41467-025-61201-6